Okay, today we are going to problem 22 and 23. A spherical hole of radius A in a conducting medium can serve as an electromagnetic resonance cavity. Assuming infinite conductivity, determine the transcendental equations for the characteristic frequencies omega Lm of the cavity for TE and TM modes. Because of the spherical symmetry, it is natural to describe the modes of the spherical cavity in terms of a vector spherical wave expansion. These waves fall into either TE or TM modes, depending on whether R dot E equals 0 or R dot H equals 0 respectively. The TE modes are given by equation 1. Here we are chosen the spherical Bessel function J1 of Kr, since it is regular at R equals 0. For a perfect conductor, we impose the boundary condition H vertical equals 0 or E parallel equals 0 at R equals A. More precisely, we demand R dot H at R equals 0 has to be 0. R cross E at R equals A has to be 0. These are equivalent to the condition JL of Kr equals 0 and leads to the quantization KNLM equals XLN over A, where XLN is the n-order 0 of the spherical Bessel function JL. The TE-NLN frequencies are thus: omega NLN equals XLN times C over A, JL of XLN equals 0, and L larger or equals 1, and M has to be less than L. Each frequency specified by L and N is 2L plus 1, fourth degenerate, with azimuthal quantum number labeled by M. The TM modes are similar. The modes themselves are given by equation 2. This time, the H vertical equals 0 boundary condition is automatic, while the E parallel equals 0 condition gives below. It may be simplified using this relation. With V equals JL of Kr times XLM and R dot XLN equals 0, we have the relation like equation 3. Therefore, the E parallel equals 0 boundary condition leads to the TM-NLM frequencies. Omega NLN equals YLN C times C over A, and the XJL of X dx at Z equals YLN has to be 0. The YLN corresponds to zeros of X times JL of X dot, or equivalently JL of X plus X times JL plum of X. Problem B. Calculate numerical values for the wavelength lambda Ln in units of the radius A for the 4 lowest modes for Tin and Tm waves. The numerical values for the wavelengths are obtained from the zeros xln and yln. For TE-NLN modes, the first 4 zeros of JL of X are X11, X21, X31, and X12. Since KNLN equals XLN over A and lambda NLM equals 2 pi over KNLM, we have lambda LM over A equals 2 pi over XLN or below. All these modes are 2L plus 1 for degenerate. For Tm NLM modes, the first 4 zeros of k times JL L of x plum are y11, y21, y31, and y41, with corresponding wavelengths are below. Note that the next mode, given by y12, is nearly degenerate with y41. Problem C. Calculate explicitly the electric and magnetic fields inside the cavity for the lowest T and the lowest Tm modes. The lowest T and Tm modes both have L equals 1. Thus, we begin with an overview of L equals 1 vector spherical harmonics. It is natural to write the angular momentum operator L in terms of rising and lowering components. Use a relation for L equals 1 gives the equation 4. A vector with components v plus, v minus, vz can be converted to spherical coordinates vr, v theta, v phi, according to the relation below. Using the explicit form of the spherical harmonics, then the equation 4 turns out below. For equation 1 for TE-NLM modes, we have E11M equals Z0 JL of KR times X1M, and H11M equals minus I over Z0 K times curl E11M. The M equals 0 modes is E110 equals I Z0 times root 3 over 8 pi times JL of KR times sine theta, and H110 as below. Note that we have used the spherical Bessel function identity. Even more explicitly, we have the relation below. Then the M equals 1 moles is given by equation 6, while the M equals minus 1 moles is given by equation 7. We now turn to the lowest Tm mode, which is the Tm11M mode with fields given by equation 2. H11M equals JL of KR times X1M, and E11M equals IZ0 over K times curl H11M. The roles of E and H are interchanged between the TE and the TM modes. In particular, the TM11M fields may be obtained from the TE11M fields of equation 5, 6, and 7 through the substitution. E turns to Z1 times H, and the Z1 times H turns to minus E. This is the action of electromagnetic duality. The TN11M modes correspond to the relation below. So the wave numbers of K NLM are quantized differently for the TE versus the TM modes. Problem 23. The spherical resonant cavity of problem 22 has non-permeable walls of large but finite conductivity. In the approximation, let the skin depth delta is small compared to the cavity radius A. Show that the quality factor of the cavity defined by equation 8.86 is given by Q equals A over delta for all T modes and Q equals A over delta times 1 minus 1 minus L times L plus 1 over XLN squared for TM modes. Energy density U equals epsilon 0 over 4 times E squared plus mu 0 over 4 times H squared, and energy is equally distributed between E and H. Thus, for TE modes, we may immediately write down energy density equals epsilon 0 over 2 times E squared equals mu 0 over 2 times JL of KR squared times XLM squared. The stored energy equals below. So we can write down the ULMN. The power loss is given in terms of the tangential magnetic fields at the conducting surface. P equals 1 over 2 sigma delta, and integral R cross H squared over the surface. Using H equals minus I over K and curl JL of KR times XLN, we can write down the PLMN equals 1 over 2 sigma delta times JL prime of XLN squared, where Ka equals XLM and JL of XLN equals 0. That implies QLMN equals omega ULMN over PLMN, and the result is A over delta. Where alpha n is the n-order positive zero for xp times JL of x prime equals 0, setting p equals 1 for TM modes, and using the notation YLN to denote the unordered zero of xp times JL of x plum equals 0. The expression for the stored energy becomes below, and the power loss result in s squared over 2 sigma delta JL of ymn squared, and the Q factor equals A over delta times 1 minus L times L plus 1 over yln squared.